Now we're going to start a new chapter. We're starting, I think it's chapter 13, Conjugated Unsaturated Systems. And this is just an example of a molecule with multiple alkene functionalities. And what you'll notice is that these double bonds, it's a double bond, single bond, double bond, they're alternating. That's what we talk about when we talk about conjugated pi bonds, where we have alternating double single bond systems. We'll see a little later the definition is actually a little bit more precise than that. It actually involves what we call the pi system. On this same molecule, we see another double bond over here. Notice that there's an sp2 hybridized carbon, sp3 hybridized carbon in between these sp2 systems. So this we talk about as being an isolated pi bond. If we think in terms of communication, we have a series of sp2 hybridized carbons. And that's really what gives us this conjugation when we have a series of p orbitals that can communicate with each other with no interruption. So these pi bonds communicate with each other. These electrons know these electrons are there. They can flow between this whole system. Over here, these electrons can't communicate with these pi electrons over here because the pi system is interrupted by this group here, which has no p orbitals, thus no pi system on that particular carbon atom. So our diene systems, there's three types of dienes that we talk about. Here's our conjugated dienes, and they can be very big conjugated systems. This is an isolated diene because the pi systems can't communicate with each other. And this one, they can communicate with each other. And this is what we call a cumulated diene. Okay? So this one, our carbon-carbon double bonds are right next to each other. Now, we're all used to talking about hybridization. We talk about this being sp2 hybridized and this being sp3 hybridized. This is sp2, sp2. What's the hybridization here? Is it sp2, sp3, or sp? It's sp. It is sp. The other thing that we need to realize about this particular pi system is that it's orthogonal to each other. That is, those two pi systems are at 90 degrees. If we think of this molecule, because of that, this can actually be a chiral molecule because the hydrogens are not both in the plane of the board. If I put this one in the plane of the board, these hydrogens are sticking behind and in front of the plane in the board. And that's because if you think about our pi system, this carbon, which is sp hybridized, has two p orbitals left for bonding, one in the plane of the board and the other sticking kind of out of the plane of the board. And I'm going to try and convey that this way. Hopefully you can see what I mean. These p orbitals are supposed to be sticking in front of and behind the plane of the board. Okay, so this pi system doesn't really communicate with this pi system. Because in order for pi systems to communicate, they all have to be in the same plane. And that's another thing we're going to talk about. I'll mention it today. But if you have time, over the Christmas break, you should look at, over the study week, remember it's not spring break, it's study week. Over the study week, take a look at conjugated systems, pi molecular orbitals, extended pi molecular orbitals, conjugated pi systems. Those are all Google terms you might want to try. Try Google Images and just Google itself and take a look at those things. So let's take a look at these conjugated pi systems. If we take a look at these, this is a conjugated system and this is the isolated system. We can hydrogenate these. This is a reaction you learned last semester where we just take double bonds and we react it in the presence with hydrogen and some catalysts, usually a noble metal catalyst, palladium, platinum, and hydrogen just adds across the double bonds. And we have an unsaturated system, and we can put more hydrogen onto it to get a completely saturated system. I've already told you these two things, they're isomers of each other. This is 1, 2, 3, 4, so we talk about it as being 1,3 pentadiene. This one is 1, 2, 3, 4, we talk about it as being 1,4 pentadiene. This is isolated pi systems. The two pi systems can't communicate with each other. This one is a conjugated pi system. They can. This reaction turns out is exothermic. It gives off heat when the hydrogen is added to the carbon-carbon double bonds. And we can measure that heat, and we can get the enthalpy for the reaction, the heat of the reaction. Notice that we just have isomeric systems. The product is the same. So the product is going to be at the same energy level. We might expect that the energetics for these reactions, that is the heat of this reaction, would be the same. We have this table's in your textbook, and here we see the trans 1,3 pentadiene gives off 226 kilojoules per mole. The 1,4 pentadiene gives off 254 kilojoules per mole. So this one gives off a lot more energy when you do the hydrogenation than this one. And if we think of it in terms of an energy diagram, where we have delta H up here, and we know that both products give this, and our this one is lower in energy. On this side, our conjugated system must be in lower energy because it gives off less heat for the reaction. This one over here gives off more heat, so it must be higher in energy. And if we want to think about this in terms of stability of the systems, what we're saying is that this must be more stable than this, okay? Now, if we go back to last semester and think about heats of hydrogenation, you talked about this before, and we talked about how different isomers of alkenes have slightly different heats of hydrogenation because they're slightly different stabilities. And the more substituted an alkene, so this one only has one substituent on it, this one has two substituents on it, this one has two substituents on it in the transposition. This is the most stable of these three isomers. It differs from this one by about 5 kilojoules per mole, and this one differs by about 7 kilojoules per mole. So between here and here, this is about 12 kilojoules per mole more stable. If we go back and take a look at our heats of hydrogenation, this is 26, 27, 28 kilojoules per mole. That's considerably more stable than the stability we got here. So is the extra stability for our 1,4 pentadiene due to the different substitution, or is it due to something else? Well, relative stabilities of alkenes, we talked about the most substituted being the most stable, relatively speaking, and the least substituted having the highest heats of hydrogenation. So let's take a look at this from another perspective. Let's do a bit of a thought experiment so we can get our heats of hydrogenation. If we take one butene, 2 molecules of it, and we hydrogenate it, we'll use 2 equivalents of hydrogen, and we get butane as our product. So we could take this molecule, react with 2 molecules of hydrogen, and we would end up getting the same product. So we have twice as much of this. We can do this experiment, and what we find is that in order to add 2 moles of hydrogen to this isolated system, it gives off about 254 kilojoules of heat. To add 2 moles of hydrogen to these two systems gives off about 239 kilojoules of heat. There's a difference of about 15 kilojoules per mole there. So again, this is our energy here. We have delta H, and what we're saying is if we have 2 moles of this and we add 2 moles of hydrogen, we get 254 kilojoules. 1 mole of this plus 2 moles of hydrogen, we'll end up getting the same product, the number of moles of hydrogen. Obviously, in this experiment, we have to have 1 mole of this, but we're adding 2 moles of hydrogen to it. So there's a difference of about 15 kilojoules between these two systems. Okay? We talk about that as being the stabilization energy from conjugation. We can do another experiment where we kind of do a similar thing. We can hydrogenate 1 pentene and 2 pentene, and we get 2 molecules similar to the first experiment, or the last experiment we just did, similar to this experiment. And then we can hydrogenate this. And again, similar system, we also find that we have 15 kilojoules more stability in this system. So this is the expected value if there were no stability, and this is the actual value that we get when we do the experiment. So there's a difference of about 15 kilojoules per mole. So these systems appear to be more stable than we might otherwise expect if they were isolated. So a bunch of experiments there, and oops, if we go back to this experiment showed considerable difference between the heats of hydrogenation here, about 26. So some of that is due to the isomerization. In fact, we have a trans double bond in that one, and that gives us some extra stability. But it does seem pretty clear that our conjugated systems are more stable than we might otherwise expect. So this extra stability we attribute to the fact that they're conjugated system versus isolated systems. So there seems to be some stability inherent in the fact that those pi systems can communicate with each other. Conjugated systems, we find them all over the place. Carotenes, everybody knows you're supposed to eat your carrots. This is important in vision. This molecule gets converted by the body to systems that are, I think there's a mistake there, to systems that are important for vision. Lycopene is, this is an interesting molecule. Notice here, this particular natural product has an extended pi system, and it's what gives tomatoes that red color. Lycopene happens to be red, and we're gonna find out why these conjugated systems give us color, why we can see the electromagnetic radiation that can get absorbed by these compounds, because we change the energy between the highest occupied molecular orbital and the lowest occupied molecular orbital. The energy difference between those two orbitals is much smaller in conjugated pi systems, and we'll learn why that's the case. A conjugated system involves at least one atom with a p orbital adjacent to at least one pi bond. So we need 3 p orbitals in a row. That's when we start talking about conjugation. 3 p orbitals that are in a row and all in the same plane can give us conjugation. Here we have a conjugated diene. We have 1, 2, 3, 4 p orbitals that can combine to give us this pi system. Allylic radical, all sp2 hybridized carbons. Another way to think of it is I need all sp2 nsp hybridized carbons communicating. They also don't have to be carbons. Here we have an enone. This is a conjugated pi system where our carbon-carbon pi system is conjugated with our carbon-oxygen pi system. E9 also we have, here we have a pi system that's conjugated with one pi system, and the other pi system of this E9 is orthogonal to it, right? Because our 2 pi systems have to be orthogonal in a carbon-carbon triple bond. allylic radical, allylic cations, allylic anions. Allylic just means a pi system with another carbon. We talk about this as being allylic. In any molecule, when we have carbon-carbon double bonds, okay, here we have cyclohexene. We talk about if we look at this molecule, there's 3 different types of hydrogen on it. We talk about these as being vinylic hydrogens. Because they're bonded to the vinylic carbon. Vinyl, you guys all know about vinyl. You can get vinyl clothes. It's a polymer. It comes about by polymerization of carbon-carbon double bonds. So the carbons that are in the double bond we talk about as being vinylic, and these are allylic. And these ones would be neither vinylic or allylic. If we wanted to distinguish them, we might call them aliphatic. There's other things we could call these ones as well. Okay, that would be a good midterm question, is to draw a molecule like that and ask you to label, identify the different hydrogens and label them. Okay, so I would expect to see vinylic and allylic, and then probably aliphatic or some other description. The important thing about these ones is they're neither vinylic or allylic. Okay, so on this allylic cation, we talk about this as being the allylic carbon. We also have vinylic carbons as well. Another interesting find experimentally many years ago, this is an interesting reaction that's actually, there's still some controversy over it, but I'll talk about it. Used to be that we talked about the hydrolysis. How many people think they know what a hydrolysis reaction is? Okay, nobody? Hydrolysis, we're just talking about the addition of water to a molecule. But when we say hydrolysis, we think of water as being more or less the solvent. We also talk about solvolysis reactions. Sometimes we'll do a reaction in methanol, and we add methanol across the double bond or something like that. We talk about that as being a methanolysis or a solvolysis. Hydrolysis is specific where water is our solvent and water is taking part in the reaction. It's we're lysing one of the hydrogen-oxygen bonds in water. So in this particular reaction, we're reacting water. We actually end up adding the OH to one carbon, and the HCl comes off. So it's a substitution reaction. What do you know about Sn1 and Sn2 reactions? So we have, it looks like a tertiary alkyl chloride. Do we get Sn2 reactions with those? Do you remember from last year? We're told that we don't, okay? We're told that we don't. Under these conditions, we expect to have Sn2 type of conditions because we have base in there. Our actual nucleophile in this case should be OH minus because we have a pretty good base, sodium carbonate. What we find is we get substitution at what was the carbon that contained the chloride, okay? And we also get substitution over here at the other position. How do we explain that? Now what's even more interesting, take a look at those product yields. If instead we start with this molecule, we get not only the same products but the same distribution of products. Okay, so how do we explain that result? As I told you, there's a little bit of controversy over this. This is the way we used to explain it, and many people still do, is that we can just have our chlorine leave with its electrons to form a carbocation. This is the carbocation we expect when it leaves. But there's a delocalization of this pi system because we have a conjugated pi system. We have 3 sp2 hybridized carbons all in a row, and we can draw a resonance structure where we just move the carbon-carbon double bond from here over to here, and we get this. This is an allylic carbocation. And it's a resonance structure. Remember, these are not single chemical entities. The real allylic carbocation has a distribution of positive charge. And they used to talk about, if we took a look at this and we see that we have 85% substitution on the left and 15% on the right, we would say, you know, roughly maybe this is a better contributor to the real structure of the allylic cation. And it is what we expect because we expect tertiary carbocations to be more stable than primary carbocations. But this is not an ordinary primary carbocation. It has the stability due to resonance. Okay? So that's a possibility. Another, how we often talk about it now is that it actually may be an Sn2 reaction. And that easily explains one structure. And we could explain it thusly. Oops. Okay, that would be an Sn2-like reaction. And this one over here let's do it this way. This would be an Sn2 mechanism. Sorry. Okay. As it turns out, this is much less sterically hindered than an ordinary tertiary carbon center because of the pi system. This kind of gets out of the way, and we don't have anything blocking from over here. So current thinking is that the reaction actually occurs by a combination of these two mechanisms. There's still some argument as to whether or not it occurs through the allylic carbocation. Okay, so this is just telling you that there are still discoveries being made and still questions being asked. So let's go back and talk about some factors that stabilize carbocations. Hopefully we remember from last semester, methyl carbocations are the most unstable of carbocations. As soon as we start replacing hydrogen atoms with alkyl groups, we start stabilizing that because alkyl groups are electron donating relative to hydrogen. And whenever we talk about things being electron donating or electron withdrawing for their inductive effects, we're talking about it relative to hydrogen. So that's something you want to remember. So that alkyl groups and I'm going to now distinguish inductively. And inductively is what we talk about as through the bond. When we talk about electronegativity, we're talking about its inductive properties. So something that's very electronegative will withdraw electron density through the carbon-carbon, or through the sigma bond. We talk about that as being inductive. So we can increase stability by increasing the substitution on the carbocationic center because we have that positive charge, but when we put alkyl groups, it's pushing the electrons in the carbon-carbon bond a little bit closer towards that positive charge, which has a stabilizing effect because positive charges get stabilized by negative charges getting closer to them. Adjacent carbon bonds, adjacent carbon-carbon pi bonds stabilize carbocations. So this is more stable than this. This is an allylic type carbocation. This is even more stable. This is more stable because in the resonance structure, we have one resonance structure which we can think about as being a tertiary carbocation. This would only be a secondary carbocation when we draw the resonance structure. So here we see this is this system. We can draw a resonance structure. These two compounds are more or less the same, both secondary in nature. This one, the resonance structure where we have the positive charge over here and a carbon-carbon double bond there, would contribute more than this one. These particular ones this is like an allylic system, and we're going to talk about this later. This we talk about as being a benzylic system. Here we have a carbocation center next to an aromatic pi system, and we're going to talk about that in the next chapter. So this then is charge delocalization. It's the stabilization through charge delocalization, and we talk about this kind of thing as being well, I'll talk about it with the next one, the next system. But it's through delocalization that's different than it's electron withdrawing, but it's electron withdrawing through resonance. We get the same thing. We can think about the same thing here. Adjacent to some atoms with lone pairs stabilize carbocations. So a good example of this, besides the ones that are up there, oh, let's leave that. So oxygen I can draw a resonance structure for this carbocation where I just move my electrons down there. We talked about this already when we talked about activating carbonyl groups. So we're stabilizing our oxygen in this case, even though an oxygen is electron withdrawing inductively, but it's also electron, we talk about it being electron donating mesomerically. So it's, even though that should destabilize it through resonance, this effect is more important. So oxygen atoms with lone pair are E-donating. Through resonance. I'll put this up. And when we have electron donation through resonance, we talk about that as being mesomeric stabilization. Okay? So all of these systems, we can take our lone pair of electrons, and that's because that lone pair of electrons is in an orbital that's very much like a p orbital. If we use valence bond theory, we even talk about it being p orbital, and that p orbital can line up with the empty p orbital of the carbocation because that's sp2 hybridized. Although we think of that as being sp3 hybridized, that lone pair is very much in an orbital that can take on p character. So we can do our resonance stabilization and donate that pair of electrons to a carbon nitrogen double bond system, and then our positive charge ends up on the nitrogen. So we get delocalization amongst the two atoms. The same thing with the allylic systems. Allylic groups, we have, that should be atoms with lone pairs, and pi systems are also mesomeric contributors, electron donators. I want to point out, you'll notice in the book that I point to a website, and he talks about even though chlorine is very electronegative, the lone pair can still form a pi bond. As it turns out, chlorine is quite electronegative, and its electronegative contribution, its inductive contribution, is greater than its mesomeric contribution, and chlorine actually ends up being destabilizing to carbocation charges. So I just want to point this out because this website, although this is valid, this isn't a big contributor to the resonance structure, to the overall structure. This resonance structure is not a big contributor to the overall structure of this system, and that's because we have to be very careful. Although this may be true, the effect is small because of the poor energetic overlap. The chlorines are in a electron pair are in a 3p orbital, and they're contributing to the carbon 2p orbital. So we have poor energetic overlap between a 3p orbital and a 2p orbital. When we talked in intro chem about how we can do make molecular orbitals, we get poor overlap between a 2p and a 3p orbital. We get much better overlap between a 2p and a 2p orbital. So that this is, I just again want to point out, mostly we don't talk about this, but this particular website does point out that this is certainly a possibility, but chlorine is very much more important inductively. Its electron withdrawing through induction is more important than its electron donating through resonance. So resonance is a valence bond description of electron delocalization. If we take a look at our allo system, we can use resonance arrows, and here we have a double-sided curly arrow to indicate that the electrons are delocalized between this carbon atom and this carbon atom. We can put the charge there, or we can do a thought experiment and move our electrons and get the positive charge over to this carbon. Remember, this exists only on paper. The real structure is not resonating between these two structures. The real structure has this charge dispersed over those two carbon atoms. This also happens with radicals. We can delocalize single electrons through resonance. Now we use the single-sided fish hooks, although it doesn't appear very well. These are supposed to be single-sided arrows, and we move these one at a time. And we can delocalize this system. So that lone pair of electron, and we talk about spin density. Remember, electrons have that spin quantum number, and it's plus a half or minus a half. And whenever we have two electrons in one orbital, they have to have opposite spin quantum numbers. When we have just one electron, we have overall spin in our system. And we talk about this as being a delocalization of spin. So these radicals react as if the radical is diffuse and maybe at this carbon atom, or this carbon atom through delocalization. And we can draw the different resonance structures. I didn't keep drawing the arrows because it gets very confusing seeing all those little half arrows. But remember, when you are talking about delocalization of radicals, when we're doing radical reactions, we want to do these half arrows. And even if we think about a hydrogen abstraction reaction, you talked about radicals. That's a chlorine atom. Chlorine atoms have 7 valence electrons. They have a net spin because they have an odd number of electrons. One of those electrons is unpaired. And we can and that's why now we draw our arrows in between. We're showing that we're forming a bond between this chlorine and this hydrogen, and we end up with the spin is now on the carbon atoms. Okay, so that is the valence bond description of electron delocalization. So relative carbocation stability, let's get to that. There is some discrepancy still. Some people put the allylic as being more stable than a tertiary. These two are close in stability, but probably, at least with these particular systems, this tertiary carbocation is slightly more stable than allylic carbocation, but allylic carbocations are more stable than secondary. So now we throw those in. This is a more stable carbocation because we now have a substituted allylic, and we get the added stabilization of this alkyl group, which is pushing its electron density towards that positively charged center. But this one too, remember that for these two, that positive charge is delocalized over the allyl system. And then if we have extended pi systems, that charge can be spread out over even greater distance. And the more we can disperse a charge, the more stable our system becomes. There's another way of describing this. So go back and think about when we talked about pi bonds initially. Pi bonds, the way we construct them, we use an MO approach. We have two, in this case we have two carbon atoms that have p orbitals with an electron in them. Those can combine through an MO description, and they can combine in what we talk about as constructive interference, and we form a bonding orbital. At the same time, we form another orbital in a destructive interference type of fashion, and we get an anti-bonding orbital. So if we can put both of our electrons in here, this is lower in energy, this is stabilizing. This one is destabilizing, and if we have to put electrons in there, it destabilizes the system. So this is bonding, and this is anti-bonding. It's actually repulsive. So two p orbitals combine to make two new orbitals, one bonding and one anti-bonding. As it turns out, with the molecular orbital theory, we can combine lots of orbitals. We talk about the linear combination of atomic orbitals. If we have 3 p orbitals in a row, we can combine those to make 3 molecular orbitals. And we combine them in such a way that we can combine them so that the p systems all overlap. This is a bonding orbital. We can combine them in such a way that we end up having no orbital density over that middle carbon, and these two. So even though this appears to be an anti-bonding orbital, it's only very slightly anti-bonding because they are so far apart. We talk about that as actually being a non-bonding orbital. And then we can combine all 3 with anti-bonding interactions in between each of the p orbitals. And this one we talk about as being anti-bonding. Where we have a change in phase, and we indicate phase either with color or we use plus and minus signs. I like color better because we don't want to confuse the phase, the plus and minus signs on these, with charge. That has nothing to do with charge. That's the phase from the wave function. So whenever you have waves combine, if they have a different phase, they don't like to combine. Wherever they overlap, they will destroy each other. And if we take a look at these, we have nodes in between. When all of our phases line up, we have no nodes on top. There is a node going from here to here. That's because we have a change in phase. Now when we combine these two, the molecular orbital looks something like this, and we have a change in phase on going from here to here. So there's a node at that carbon. For this one, we have a change in phase going from each of these. So we actually have 2 nodes in this plane. Don't forget there's always that node that's there because they're p orbitals. But these nodes are orthogonal to the other node that goes through the plane of the board. And when we do this combination, the energy level of our p orbital would be about here. When we do the combining, these are lower than the original p orbitals. In energy, this is higher than the original p orbitals, and this is not much different. We talk about it as being non-bonding. So with our allylic system, we're just talking about the electrons in the pi system. With an allylic cation, we have 2 electrons in this pi bond. If we were thinking just of, let me draw a cation. Okay, so we have 2 electrons in that pi system. In this p orbital, because it's sp2 hybridized, there's no electrons in that p orbital. It's an empty orbital, but it can combine, and our electrons can now go into the new system and be delocalized over that whole system. As it turns out, and this is where we will, as it turns out, we can continue this. So we have a p orbital. Then if we have carbon-carbon, 2 sp2 carbons bonded to each other through a sigma system, but they have those p orbitals, we have our pi system. We have a pi and a pi star orbital. Then when we have 3 p orbitals, we can combine them like this. Notice that there's always this carbon that has no electron, no orbital density around it. When we go to 4, we have a pi system. This is bonding. This actually is slightly bonding. All of this indicates our p orbital level, so everything below here is bonding in character, and everything above here is anti-bonding in character. And as we get extended pi systems, you can see that we end up getting stabilization of our entire pi system because it's conjugated. So from that valence bond description, now we're talking about an MO description. And conjugation, is this conjugated? We know that's conjugated. This is isolated. What about this system? This system is, actually turns out it is conjugated. All of these systems are conjugated because we have p orbitals there. And we have 5 p orbitals in a row. So they are. So this particular thing, our carbocation, because we have an empty p orbital that's sp2 hybridized, we have an extended pi system. Same with ions. And notice now, we talk about this as being an extended pi system because we have an oxygen in there with a lone pair of electrons. That lone pair of electrons has to exist in something. It exists in, if we use valence bond description, we talk about it being in an sp3 hybridized, but it's really more like a p orbital, and so we have an extended pi system. And as long as we have an extended pi system, we have conjugation. Notice now when we talk about having methylene group in there, our carbon is sp3 hybridized, and there is no communication between these 2 systems. Here's a case where we have nitrogen positively charged, but it's sp3 hybridized because we have 4 bonds to that nitrogen. So this also is not a conjugated system. Take a look. There's a link to the website where I robbed that. And whenever I rob something from the internet, I try to remember to put the link in. So that's where we're going to end for today. I gave you 3 extra minutes. So have a good study week. And I'll have your